All right, that was 15 minutes. We still got time. All right, we might wrap up a little early so I'm not standing here until lab time handing back tests. Okay, interesting insect for the day. Rocky Mountain locust. So we talked about this guy just briefly in lab, and I wanted to talk about him today because I think it's a really interesting sort of pest that we had here in North America that's no longer a problem. These guys are orthopterans, so they are, grasshoppers, and they are in the family Acrididae, meaning that they are the short-horned grasshoppers, so they look like the traditional grasshoppers we expect to see. Now, these guys are what is a now extinct pest. They used to be a major problem in the Rockies and the Plains states, primarily because these guys had the type of Acrididae life cycle where they could go into a gregarious locust phase, meaning that while normally these grasshoppers would just hang out in the field, they'd chew on, a handful of plants, mind their own business, would ignore other grasshoppers. If put under the exact right conditions, these guys would go into a hyper-reproductive, hyper-social, highly migratory life phase that would form swarms that would basically fly across the western United States, devouring any crops that they could find. And consequently, in the early 1800s, this was really a major plague to a lot of the early settlers who were coming west of the Mississippi to settle all the new lands that were becoming available. And consequently, they also are sort of an interesting story because they used to be a huge problem for about 30 years, and then they just disappeared without a trace, and nobody really knew exactly what happened to them. So functionally, what was going on is, like I mentioned, normally Rocky Mountain locusts lived in the Rocky Mountains, as the name would suggest. They would hang out in a solitary phase, basically hopping around in Rocky Mountain meadows, feeding on the plants. But whenever a periodic drought would come through, all the plants they fed on would start to dry up. The locusts, the grasshoppers, would start moving closer and closer to the streams that had on the water where the green plants were left. And as they got close to one another, they would start going through this transition from a solitary phase to a group or a social phase. And they would develop these stronger flight muscles. They would become gregarious, meaning they'd like to hang out in groups instead of by themselves. And they developed a desire to get out of Dodge. They didn't want to hang out in these valleys that were all dry. They wanted to fly out somewhere where there was food. And what they would do is they would migrate east into the Great Plains. Now, back in the 1800s, the US government had a policy in place where basically if you wanted to move west, they would give you a parcel of land that you could live on. And if you lived and farmed it for a certain amount of time, I think it was 10 or 15 years, they would just give it to you. It's basically their way of encouraging people to move out west and develop. And so basically these people moved out, started planting their crops, making their homesteads, and all of a sudden they had these huge swarms of locusts landing on their land, chewing everything down to the ground. And some of the stories are really outrageous. They tell these stories about people basically coming out. They would hear this sound, sort of like a hailstorm, just grasshoppers banging off the walls of their houses. They would come out and there would be grasshoppers just crawling all over their crops. They would be eating the wooden handles off of their tools. They would chew the clothing off of clotheslines. They just ate everything they could find, just decimated. Oh yeah, and stories of supposedly grasshoppers crawling all over sheep, eating their wool down to the skin too. So really, really bizarre stuff, kind of a real true plague. And and so there were these just all the time. And then the worst thing was that when they landed and they fed on the crops, they would also lay eggs in the ground. So that a couple weeks later, all of a sudden you'd have all these grasshopper nymphs popping up out of the ground to eat whatever you had just planted in the meantime to make up for the loss of your crop. And there's also all these weird stories that these nymphs, they can't fly, right? But they're still migratory, so they form these great big long, basically nymph rivers that would crawl across the landscape from farm to farm looking for things to eat, just marching on foot. And they would even try and cross rivers. So they kind of crawl over one another into the water until they formed a living bridge across the river to get to the other side. So these guys were kind of impressive in a horrifying sort of way. Of these swarms, one that was particularly notable was Albert's swarm in 1875, and it's called Albert's swarm because Albert Child measured the size of it, and it's considered to be the largest swarm of insects that's ever been recorded. He basically went out and he timed basically how long the locusts flew over his house, which was more than a day, and he estimated about how fast they were moving, and he talked to a bunch of people that were down the rail line from him and got communications on the telegraph of when the swarm had hit their towns, and he could use that to estimate the speed as well. And basically, the estimated size was just shy of 200,000 square miles, which comes out to like 27 million tons of locusts, causing about $200 million in damage, which would be 4.4 billion in 2016. So a lot of damage, a lot of locusts. And that's the estimated size of the Albert swarm. So bigger than the state of Nebraska. This was a serious entomological problem. Consequently, this was where Charles Valentine Riley got his start. He became the entomologist in Missouri, and he got appointed by the USDA to be the head of a commission to study Rocky Mountain locust. So that was kind of his big step up into the national scene. But yeah, so this is all happening in the late 1800s, and by 1902, nobody could even find the species. They'd go up to the mountains and look for it, and it was completely gone. And it was kind of this big mystery as to what happened. And a mixture of things happened. Part of it was that growers figured out which crops the locusts really liked, and they stopped growing them. They started growing things that locusts didn't like to eat very much. So that when the locusts showed up, they would stop down, feed, and then kind of fly away before they consumed the entire thing to the ground. And also, a big part of it was that people started settling down in the Rocky Mountain valleys, and they started actually farming them. And so you had all these places where the locusts were sort of living during regular years. They were laying their eggs, feeding on the meadows, and all of a sudden you've got settlers coming in and plowing up all their eggs, tearing up all the vegetation they used to eat and planting their crops. And this just really knocked the populations down until they went extinct. So there are some people who think they're still crawling around up in the mountains, but it seems unlikely that we're ever going to see anything near the sort of swarms that we used to have back in the 1800s.
You mentioned once they started to get close, they start migrating together.
Mm-hmm.
Is there ever a stage where they start to become independent again, or they just choose to be by themselves?
Eventually, they will get to a point where what they will do is they'll, at the end of the season, so at the end of the seasonal cycle, which we'll talk about in just a minute, basically climate will trigger them to go into a reproductive phase for overwintering, and so they'll turn around and fly back to the Rockies, and they'll lay their eggs in the meadows that are out there. But yeah, so that brings me to an interesting point. And by an interesting point, I mean what we're actually supposed to cover in class today. So last Wednesday, we covered the life cycles. So we talked about the instars, the shedding of skin, going through the process of egg to nymph to adult stage. And basically, that's the whole idea of a life cycle. Now, from an economic perspective and from a greater ecological perspective, though, many insects don't just have a life cycle that they go through, but they also have a seasonal cycle, or the progression of one or more life cycles over the course of a one-year period. So basically, how do insect life cycles time out to the changing of the seasons? Now, generally with insects, what we find is that life cycles are extremely tightly linked with the environment. And this makes sense from the perspective that insects are cold-blooded. So they're going to be the most active when it's warm, and they're going to be very inactive when it's extremely cold outside. And as such, in temperate climates where it gets very hot and very cold, insect life cycles basically follow the changing of the seasons, such that they can basically take advantage of resources when they're available and they can go into some sort of hibernation, what we call diapause, whenever conditions are unfavorable. Now, in temperate areas, oftentimes insects are what we call univoltine, meaning that they have a single generation every 1 year. So basically they go through egg, nymphs, and adults one time in a calendar year, or more accurately, one time during the warm season. And what's nice about these univoltine populations is more or less that all the insects are in the same growth stage at the same time. And it makes them really easy to predict, and it makes it nice for the purposes of management. And this is pretty common amongst things like grasshoppers, rootworms, things that have a soil-borne life stage, given that soil temperatures are usually pretty regular, even between years. However, many insects aren't truly univoltine, they are what we call multivoltine, meaning that they go through more than one generation per year. They're completing multiple life cycles within a single year. So here, basically we have this little figure that just shows the length of a seasonal cycle. Here, SC versus the length of a single life cycle, LC. And so basically, right, in a univoltine system, the life cycle is the same as the seasonal cycle, whereas in a multivoltine system, the life cycle is considerably shorter than the seasonal cycle. So you may get 1 to 3 generations in the course of 1 year. Now, what's tricky about multivoltines is that at the beginning of the season, when the insect is emerging from its overwintering, when it's basically coming out for the first time looking for something to eat on, we'll have sort of a nice, tight coordination of life stages in the insect. Really easy to predict. So what we have here basically is time, and on the X we have the number of insects on the Y. So basically as a line goes up, that means the number of insects are increasing as we pass through time. And each of these little bumps represents a single generation of the insect. So if we were saying that over time we have here the beginning of the warm season, and back here we have the end, we see that as the insects start to become active during the warm season, the population increases, we have our first generation. And looking at it, for the most part, all we have is the one generation. Because they are all emerging from overwintering at the same time, they're all in the same life stage, nice and easy to look at. But as they start to reproduce and lay eggs, we start to see the second generation emerging, and some of the second generation is laid earlier in the first generation, some of it is laid later, so it starts to spread out. And by the end of the season, we have the 4th, 5th, 6th, 7th, 8th, 9th generations all kind of overlapping with one another in a really messy pattern. And this is why for some pests, if you go out later in the season and you look around, you'll find all the life stages. You'll find eggs, you'll find all of the instars, you'll find adults, all in the same field, all at the same time, in really kind of a messy overlap. This is something we would see really commonly with something like aphids or leafhoppers, organisms with really high reproductive rates. Now, the last type of voltinism is one that matters less from a crop perspective, but it's something we call delayed voltinism. And this is a case in which the life cycle is actually longer than the seasonal cycle. So it takes more than 1 year for the insect to go from egg to adult. This is pretty common in a handful of pest species, wireworms and June beetles. So scarabid versus click beetles. They tend to take 2 to 3 years in the soil before they come out as adults. But on the more extreme end, we have things like the 17-year cicadas, which have to live underground for 17 years before they'll reach their adult stage. And on the most extreme end, we have things like the Buprestidae. So Buprestidae are these guys right here. They are what we call jewel beetles. They bore into trees and feed on the cambium, a major pest of trees, especially in the Midwest and the East Coast. their larvae can live inside a tree just slowly growing for up to 50 years before they emerge as an adult. So a very long immature life stage. All right, so seasonal adaptations. As I mentioned before, the main point of the insect's life cycle is basically that they're trying to take advantage of resources when they're available and to take it easy and live off of those resources when times are lean. And as such, insects' ecology and how they interact with the environment is largely determined by these sort of predictable cyclic extremes. When is it summer? When is it winter? When are things actually available versus when is it bad to be out there? So for the most part, insect seasonal cycles are determined by whether the insects are in quiescence or not. Or sorry, not quiescence or not, or basically are insects avoiding activity or are they actively trying to gather resources? So there's a couple ways that insects sort of avoid inopportune times, one of which is quiescence. Quiescence basically means that the insect slows down its development due to some sort of temporary adverse conditions that are going on at that very moment. You can kind of think of this as when you wake up on a chilly morning and you see a fly sitting on the windowsill. That fly is going to be slow. You can kind of just pick it up, toss it around, because it's too cold. The fly basically doesn't have a lot of energy in its body, and instead of burning fat to generate energy and to start moving around, they're going to chill out and take it easy. They want to wait for it to get warm before they start looking for food. They're just being quiescent. Now, quiescence, however, doesn't work really well for predictable environmental extremes, such as these seasonal changes going into winter. So you can't just sit down and chill out for 3 months while it's stinking cold outside. Consequently, insects go through profound physiological and behavioral changes in order to deal with that. And we call this dormancy. So basically, there is quiescence, which is when things are bad for a little bit of time and the insect just slows down its growth. When things are going to be inopportune, bad conditions for a long period of time, talking months, insects go into a true dormancy. So dormancy being a seasonally recurring period in the life cycle when growth, development, and reproduction are suppressed. So basically, the insects find a cool place to hang out, and they just stay there, and they don't move, they don't eat, and they don't mate. Now, some insects, the time in which they want to chill out and not grow is actually summer. So during summer, we call dormancy estivation. And this is generally not as common as we see for winter dormancies. There are a handful of insects, though, that don't like hot temperatures. These guys. So it's a little hard to tell, but right here, this is a whole bunch of alfalfa weevils. Alfalfa weevils are a big pest in alfalfa early in the season. They like cool weather, so they'll show up in the early spring when the plantings are just starting to grow really well again. They'll lay their eggs. The larvae will feed on the growing shoots of the alfalfa. When they reach their adult stage, they will fly to neighboring trees. They really like loose bark stuff like eucalyptus, and they'll hang out underneath the bark until the heat of the summer has passed. And then they'll come back out again the next spring. On the flip side, most insects, though, undergo a winter dormancy, or a hibernation. And this makes sense, because if you're a cold-blooded insect, you need energy from the outside environment to carry out your basic life functions. If it's cold outside, you just don't do very well. And as such, you basically just hang out and don't do anything. Now, here in the Central Valley, it doesn't get that cold. We may get frost a handful of times over the course of the entire winter, and it's entirely disappeared by the time the sun comes out and starts baking it away. However, if you're, say, somewhere further north, somewhere a little bit more central, or you're higher up in the mountains, ice and snow can become a really big problem for insects. Because once an insect freezes, all that water that's inside their body will crystallize. And those water crystals, right, will start cutting into cells, organs, fat bodies, just start shredding up the inside of the insect and will kill them pretty quickly. That's why we pop insects in the freezer when we want to kill them for our collection. Consequently, insects have a handful of ways to deal with this, one of which is called supercooling, where basically the insect becomes resistant to freezing by lowering the freezing temperature of their internal body parts. So functionally what they're doing is they're producing insect antifreeze, and they're pumping it into their hemolymph. That way, whereas water in the insect would normally freeze at 32 degrees Fahrenheit, maybe now it freezes closer to 8 degrees Fahrenheit because they're chock full of antifreeze. The other thing they have is that some insects are actually freezing tolerant. So that means that they can be completely frozen, but they have certain physiological mechanisms that allow them to repair any damage they get from being frozen. And so they can survive it. Consequently, that's why sometimes if you freeze insects, you pop them in the freezer, you pull them back out, and they come back to life, even though they've been frozen for a while. Has anyone had an insect come back to life?
Yes.
Yeah? Right. Some insects are pretty tolerant of freezing. So, yeah, you got to pop those guys in the kill jar. All right. So when insects go into a dormant phase, they undergo what we call diapause. And diapause is the physical condition or physiological condition that actually delays that development during those periods of adverse environmental conditions. So just to be clear, dormancy is basically the actual action of going inactive during a period that's not good, whereas diapause is the physiological thing that is happening inside the insect. And what's going on during diapause is basically the insect lowers its metabolism so that it's not really needing very much energy. It has just the bare amount of energy it needs to keep going. It has little or no development. In most cases, they don't develop at all. So they'll just sort of hang out at their current life stage. They have increased resistance to these environmental extremes. So like I said, a lot of insects, when they diapause, they will produce antifreeze and put it into their blood in order to avoid damage from the cold weather. And they oftentimes will also alter their behavior. So a lot of insects will search out a sheltered place. They will find tree bark to hide under. They'll dig down into the ground. Maybe they'll crawl inside people's houses. You may notice those lady beetles, the big fat orangish yellowish ones that you get inside your house about once a year. Have people had that before? No, that's not a problem. Okay, maybe. Well, you used to live in the Midwest. In the Midwest, there's a lady beetle. We have them out here, but I think it's warm enough they don't come in winter. But as soon as it started getting cold, these Asian multicolored lady beetles would land on the sides of houses and crawl into the cracks in the walls and live in your insulation. So if you had kind of a loosely built house, they would get all up in your business all winter long. Right. And diapause can be initiated for any number of reasons. The most common one is cold temperatures, but again, diapause can be initiated for anything that is basically bad for the insect. So if it's too hot outside, if it's too dry, if they lose their hosts, they can basically enter this period and wait until conditions are better. Now, something that should be pointed out, though, is that diapause is not just some emergency reaction the insect can turn on whenever they want to. So basically, it's not like we can go up and plow up a field and all the rootworms that are in there feeding on the corn roots are going to go into diapause and wait for us to replant. Diapause has to be turned on by a recurring environmental condition that signals some sort of longer trend of scarcity is about to occur. So let me rephrase that. Basically, quiescence is a temporary change, right? The insect just sort of slows down for a little bit, then turns back on. Diapause is kind of an irreversible thing that the insect does, and it typically lasts for several months in a row. So an insect doesn't want to turn on diapause unless it absolutely knows that it's under bad conditions that aren't going to disappear for several months. Because if an insect goes into diapause in the middle of summer, it's going to wake up in the middle of winter. And it'll be in a really bad way. So the insect needs to know in some sort of guaranteed way that when it goes into diapause, that it's going into diapause right before winter, and that it will emerge from diapause right when summer is coming on. And the way they do this is that diapause is only induced by something called a token stimuli. Now, a token stimuli is some sort of environmental cue, and the cue itself is not favorable or unfavorable, but what it does is it signals some sort of long-term change that's coming in the environment. So basically, what most insects do is that they watch how long the days are. They measure photo periods. So if you're an insect out in an almond field, you're hanging out, eating some leaves, minding your own business, and there's a really cold day out of the sudden. You're not going to go into diapause because cold days aren't necessarily predictive of when cold weather is coming. Sometimes we just have random weeks that are kind of chilly in the middle of the fall, or maybe even the middle of the summer. Likewise, we can have freak hot periods in late fall or the middle of the winter. So if insects use temperature to determine when they went into diapause, they'd be in a lot of trouble. However, day length is super predictive of winter coming on. It's basically causative of winter, essentially. And so insects will watch out for day length, and typically once they hit a certain ratio of how long the night is compared to the day, they'll turn on diapause. They'll say, hey, winter's coming, time for us to chill out. And then once they enter that diapause, they have to hang out in it for a really long time. Typically, they will watch out for day length increasing. Sometimes they'll watch out for consistent temperature changes going up. Sometimes it's a combination of the two of those. But essentially, insects will hang out in diapause until conditions improve, and then they'll come out into the crops. So, what's kind of nice about this, though, is that for a lot of pest insects, we know the environmental conditions that encourage insects to come out of diapause. And as such, we can watch out for those things, and we can just basically start treating for insects as soon as they start coming out of the ground, and we can start managing their populations when they emerge from winter and they're at their weakest. So with that, I'm going to do just a tiny bit of insect ecology, and then we'll tap out. All right, so insect ecology. The reason I put this up here is that ecology is kind of a term that has been co-opted by political operators. And oftentimes when we talk about ecology, there's kind of this real mental image of people driving smart cars and, generally this sort of anti-agriculture sort of feeling. And I just wanted to basically drive home that this is not what I mean when I'm talking about insect ecology. When I'm talking about insect ecology, I'm talking about ecology in the most scientific sense of the term. That ecology is the study of interactions between different organisms, as well as between organisms and their environment. So we're talking about how do insects interact with one another, so how do pests interact with predators, and then how do organisms interact with their environment? How does, say, an irrigation regime impact soil-borne insects? Or how does a harvest period impact the pests that you have hanging out at that moment? So consequently, insect ecology is really the investigation of how changes in the environment affect the abundance, timing, and diversity of insects. And as such, if you think about it, economic entomology is really not a whole lot more than applied insect ecology. It's the question of how can we manipulate fields in order to increase the abundance of insects we like while decreasing the abundance of insects that we don't like.